My fourth type of simple chemical reaction is the double replacement reaction. And I'm going to recognize this because I'm starting with two compounds. So whenever I see compound plus compound, I'm thinking double replacement reaction. And the formula for something like this is if I have compound AB plus compound XY. Then probably the best way to think about this is your A and your X are switching spots. So two replacements are going on at once. And A and Y will now be together, and B and X will now be together. So when A and Y come together, A goes first because it's already first. It's my cation, so I'll have AY and I'll have XB. So once again, X is my cation here, so X is my cation and first over here. A is my cation and first here, so A needs to be my cation and first here. So that's my double replacement reaction. Compound plus compound, I switch spots twice. So let's look at an example of that type of reaction. So let's say that I have K3PO4, potassium phosphate, plus NaOH, sodium hydroxide. So I'll think about this as my K and my Na as switching spots. So don't worry about the subscripts right now. The best way to do this is to first just put things together. So my K is now going to be paired up with the hydroxide group, and my Na is going to be paired up with the PO4 group. Now we need to check and see if this is correct and if this is the correct formula for these compounds. So K has a charge of +1, OH has a charge of -1, so KOH is correct. If I look at sodium phosphate, as a reminder, sodium is +1, my phosphate group is -3, so when I cross and drop my charges, I get Na3PO4. So the correct answer here has to be Na3PO4. I didn't have to make any changes here because this was already charge balanced, but I needed to add this 3 in here to make the correct reaction. So just like my single replacement reactions, these reactions do not always occur, and I have to check to see whether or not this will happen. And these reactions occur in aqueous solution. So probably the best way to think about how this reaction is happening is that if this is my container of water, and I'm putting two compounds in, and here will be my AB compound, and here I'll add in my XY compound. That when AB gets added in, if AB is soluble, then the A's and the B's will break off and they'll go their own separate ways. So I'll have my little A cations floating around and my little B anions floating around. And when I add in my XY, if that's soluble, then those are going to break apart as well. And I'll have my little X cations floating around, and I'll have my little Y anions floating around. Now the new compounds we're proposing to make would be A and Y joining up and forming a compound, the compound AY, and I'm having my B and X come together to form the compound XB. But the question is that if we're still in this aqueous solution here, if I'm still in this container of water, then why won't AY just go its own separate ways when it's in the water? And why won't XB go its own separate ways as well? And the answer is that they will if they're soluble, and we won't have any product formation. So the only way we'll get product formation is if when these newly formed compounds come together, that they have a way to get out of the solution. At least one of them has a way to get out. And there's several different ways that you can quote-unquote get out of the solution. And the main ways we're going to talk about getting out of the solution are, number one, The obvious way is that you are not soluble anymore. You're insoluble. So looking at my previous example, if when X and B come together, they're not soluble anymore, well then hey, they're able to get out of the solution, we're able to form a compound. So what do we call that when it's something that's not soluble? That's called the formation of a precipitate. And that's how I will visually recognize it. And you think about precipitate like it's precipitating, it's raining down, and when you see a solid form, maybe a color change, and eventually if we let it go, it will all settle to the bottom. That's my precipitate that's forming. Another way for this to happen is that if we form water. If one of the products is water, then it just sort of sinks off into the background, and the other compound is able to be formed because it's the only thing left. And the third way that you can get out of that solution is that if you form a gas of some sort, and then you will bubble away out of the solution. So let's go back to the example of this type of reaction that we did, and that's with my potassium phosphate and sodium hydroxide. So I need to look at my solubility rules to accomplish this type of reaction. And I look at both of my reactants, and they both need to be soluble for this reaction to occur. And I'll look up potassium phosphate on my list, and I say, well, all carbonates and phosphates are insoluble except potassium is one of my exceptions. So this is a big S for soluble here, which is a good thing. That means when it gets into the water, they break apart. Sodium hydroxide, I look, well, all hydroxides are insoluble except sodium is one of those exceptions. So this is also soluble. That means that when both of these entered into this container of water here, that they broke apart. So the reaction's able to be initiated. Now, if the reaction is able to be finalized, then I'm going to look at these two products, and one of those has to be able to get out of the solution. Neither of them are water, obviously, and neither of them are a gas, so one of these needs to be insoluble for this to work. So let's look at my KOH. Is potassium hydroxide insoluble? And looking at the solubility rules, I see, well, this is actually soluble. And then I'm going to look at my sodium phosphate. It says all carbonates and phosphates are insoluble except, oh boy, this is soluble as well. So what does that mean for the fate of the reaction? That means that, all right, well maybe K and OH will bump into each other, and maybe Na and PO4 will bump into each other, but as soon as they do, they break apart again because they're soluble. So this will result in no reaction at all. So let's summarize the conditions I need. I already talked that my product needs to be either insoluble, needs to be water, or it needs to be a gas. And the final things that both of my reactants need to be soluble. And I'll sort of jot that off to the side here as a reminder. That not only does my product need to be either insoluble, water, or a gas, but both of my reactants need to be soluble. And that's a double replacement reaction. How do I recognize double replacement reaction? I recognize because I have compound plus compound to start the reaction.